in this one we're to find the area of this triangle, and the interesting thing is that we don't know this is isosceles. The picture kind of looks isosceles, but this could go more like this and then down like that. It could have the same altitude of 5 and the same base of 3 and yet be shifted over. So we have to be aware that it doesn't necessarily have to look that way, which means that we can't find the function equations for the sides of this triangle because it's not fixed. But we can still find this area because we can say, alright, we know that the base is 3 and the altitude height up to the vertex up there is 5. So we're going to set up a proportion. At a height h up from the bottom, we're going to draw a line across there right here, the width across there, which we're going to call the A. That's a width. And we see that let's put it underneath so I don't run into it. Here's your A, and here's the altitude to that base. And from similar triangles, we can set up a proportion that says that 3 is to 5. 3 is to 5 as the base here of the smaller triangle is to its height. And its height is this height right here, which happens to be 5 minus h. So 3 is to 5 as A is to 5 minus h. So that's setting up similar triangles. Now to help you see that, you can see that the 5 altitude comes all the way here. And you can see that the base 3 is to its altitude 5 as the A base is to its altitude, which is 5 minus h. Okay, so now we have this relationships solving for A, the width across. So the area of a strip, which we can see at the height h off the ground, a representative strip is right here. It has width A and it has delta h increment in the height there. So the area of that strip is A, the length across, that was A, times the delta 8 increment. And that's going to give you 3/5 times 5 minus h times the delta h. Then you're going to add all those up, going from h equals 0 on what we call the ground, h equals 0 down here, all the way up to h equals 5 up there. So these representative rectangles are going to be moving from places like this up to places like this, and then finally at the very top up there, and of course at the bottom. So move those rectangles in your mind up and down so they sweep out the entire area of the triangle. Then check the boundaries to make sure that you're really sweeping out all the area as you take your h's from 0 to 5. So over here, and h equals 0. 3/5 of 5 minus 0, that's the a. That was the a part. Checks out that it's 3. So there really is a width across at the bottom of 3. And at the very top at h equals 5, there's supposed to be 0 width across there. At the very top, there's supposed to be 0 width. So let's see. At h equals 5, 3/5 of 5 minus 5, that's the a, equals 0. That checks out. The width across at the top is 0. Now you know you have your formula right. So your area strips are 3/5 5 minus h times delta h, and you're summing those up from h equals 0 to 5. And then you take the limit as n goes to infinity for the number of subintervals, and you get your integral. We use that trick of factoring out the 3/5 because we can do it. It's being multiplied. We run the fundamental theorem of calculus, get the exact value, and it comes out 15 halves. So 15 halves is the area of that triangle. And interestingly, we've just proven that any triangle that has that base and that altitude is going to have 15 halves for its area.